Hi everyone, this is a lecture on the Fermi function, also known as the occupancy probability. Occupancy probability. I learned it as Fermi function. There we go. I preferentially use the letter F for it as Fermi function. Halliday and Resnick uses the letter P, I think, for probability, which makes sense. But it's the exact same thing. I'll try to stick to P, as that's what Halliday and Resnick uses. And so P depends on energy. Right, so we can draw a picture of different energy states. And then we have P for the probability of filling. And the idea is that electrons and fermions, most particles always want to do the low energy. Low energy, because they are lazy and they want to be as low energy as possible. And then over here at high energy, they don't want to be there. Right? So we have some probability of 100%, which equals, we're actually going to use decimals, so 1, okay, where it's at 1, that means it's totally full, so all of our electrons are basically going to fill up. Maybe this is a better color. I don't know what color that is. It's going to fill up until it's totally full, and then the probability will drop to 0. Oh, interesting. Probably drop of 0, or it's not full anymore. All right, so the Fermi, or the probability of occupancy, or the Fermi function, is that it's going to be 100% at low energies, and at high energies it goes to 0%. And we have, let's see if I can choose a different color. And where it falls down, basically this energy right here, has a special name, and that is EF, or the Fermi level, or Fermi energy. So either of those names are quite common. I think Halliday uses Fermi level. This is also somewhat related to chemical potential, as you might have learned in Gen Chem, but not quite related. So I'm going to try to avoid using that term. But if you're curious, you can definitely look it up. All right, so we have, so this is our graph of probability. It's at 100%. It's 100% filled, every energy state that's smaller than EF, right? So for energy less than EF, we have the probability equals 1, which is the same as 100%. And then for energy greater than EF, the probability equals 0, or 0%, because electrons are lazy. I don't know what my son is doing. Okay. All right, so that's the whole idea. That's the overarching idea of the Fermi function, or the occupancy probability. All right, so, but one interesting thing is, temperature, or we'll call it heat, is an energy, right? We learned that in our thermo section and thermodynamics. And therefore, if there's heat, some electrons have extra energy. Extra energy. So that means that if there is any heat, so if heat means T greater than 0 Kelvin, right? So if we're at any temperature greater than 0 Kelvin, then we're going to have, instead of having a stark contrast, right, when we draw our probability versus energy, right, before, let's see, we have our 1 on there, we have 1, 0, right, before we had a simple just cutoff right there, right, where that's EF, right, and so that's for, where should I write it, 0 Kelvin. But if you have anything higher than 0 Kelvin, if you have a little bit of heat, then what you find is you have 1, and then actually it has a little bit more gradual change, right? So at high energies, it still becomes, at very high energies, it still goes to 0. At very low energies, it's still at 1. But somewhere in the middle, you actually have, it's more gradual, right? But it always goes through half at the Fermi level. So that's actually the definition of the Fermi level. EF is where P equals 0.5. Right. Yeah. Okay. All right, so that's what is conceptually. So let's write an equation on this. So there's this whole idea. And so you have Enrico Fermi, who is in Chicago, and Paul Dirac, I believe, who was in, actually, I have no idea where Dirac was. But I know Fermi was in Chicago, and they came together and they made this equation, and they started thinking about, okay, so what if, like actually thinking about, for each electron, they fill this in, and then if they have a little bit of heat, then they make this gradual. And so from first principles, from the idea of filling in these electrons and figuring out how much heat they have, they figured out the statistics of all of this. And so some people call this the Fermi-Dirac. Some people call it just Fermi, or then they also call it Fermi-Dirac. Anyway, so textbook uses P, and the equation for this is 1 divided by E, so that's our natural number, 2.71, delta E over KT plus 1. Okay, where K is Boltzmann's constant, right? We done Boltzmann constant somewhere? I'm sure we talked about Boltzmann's constant somewhere, especially thermodynamics, right? You can do this in kind of like Planck's constant. You can have it in units of joules or in units of electron volts. Let's see, I have this written down for joules. It's 1.38 times 10 to the minus 23 joules per Kelvin. And then for electron volts, it's 8.62 times 10 to the minus 5 eV in Kelvin. I gotta write, this equation is really important, right? It has to be done in Kelvin, right? We're always going to do our temperature in Kelvin so that we don't have to worry about negative temperatures. And again, I preferentially use electron volts in quantum, in all this stuff. So we're going to use the electron volts one. And one thing that is actually helpful, a shortcut that I learned, is that KB times 300, right? Because that means that for temperature equals 300 Kelvin, right? If you have KB times 300, that's 0.026 eV, right? So that equals KBT at room temperature, or roughly to room temperature, right? Room temperature is about 300. So that's another shortcut we're going to use for Gen Phys. Actually, maybe on the homework I might give you other temperatures, but definitely for on the exam, I'm only going to give you a temperature equals 300. So that's a useful number to have and to know, right? And so we just end up with probability, right? So we get, all right, and again, probability equals 1 divided by E to the delta E over 0.026 plus 1. Again, at room temp. This one's for room. I don't know why I have such trouble writing room temperature. All right. So let's actually apply that. Oh, so what is delta E? Delta E, good question. Delta E equals whatever energy state you're talking about minus EF. Right? So that's just here we can use our color thing. Right? So EF depends on your different materials. It depends on what you're talking about. and so if we're talking about energy higher than EF, so that's our delta E. And usually I think in the Wiley Plus always it will give you a delta E, or I might say an energy above the energy the Fermi level, right? Energy above Fermi level. We will not do any energies below Fermi level, but you could easily just plug it in, you'd get a negative value in there. Sorry, I need some water. All right, so let's plug this in for some values. All right, here we are. I'll leave it like that for now. All right. Example question: what is the occupancy probability that a state at what is P at a state that is 0.045 eV above the Fermi energy? So at E minus EF equals 0.045 EV at 300 Kelvin. That's ugly outside. Okay, at 300 Kelvin. All right, so we're going to go to our question mark. Okay, so P equals 1. Oh, my throat is so dry. Okay, 1 E 0.045 over, this is at room temperature, so we can just plug in the 0.026 and then plus 1. All right, so we plug that into our computers. Let's see, 0.045. I put that in Wolfram alpha, and I got 0.15. Right, so that means it's a probability of 15%. Right, so if you're at an energy state which is 0.045 EV, which is very small, if you're basically at an energy state that's just above the Fermi level, then the probability of that being filled is 15%. All right. So there's some there, not a lot, but there's some there. Okay, and let me make a graph over here. I'm gonna delta E probability. Let's see, 0.045 EV. We got. I'm gonna leave it in decimal. Okay, let's instead do P at I'll just call it delta E equals 4.5 EV. All right, so all right, again we plug it in, P over 1 E to the 4.5 over 0.026 plus 1. I plug that into Wolfram 2. What do we get? I got 6.8 times 10 to the minus 76. Wow, minus 76. All right. 5 EV. I'm just going to write 10 to the minus 76. Right, so this is one of the really interesting things about Fermi probability is that we went up between 0.045 to 4.5. That's 2 orders of magnitude, right? 2 orders of magnitude, and we get a change of 74 orders of magnitude in probability, right? So that's 10 to the 2, that's 10 to the minus 74, I'm running out of space. And so that's a really interesting aspect of anything of electrons, basically, if we're talking about where they, the statistics of where they will be and when they'll be there, depending on temperature, and I think it's really cool. Okay, well, I want to do one more delta E. Let's do delta E in the middle. Let's do 0.45 eV, right? And for that, we get, let's plug it in. I got 3 times 10 to the minus 8. Right, so for 0.45, if we're right in the middle, we get 10 to the minus 8. Now, 10 to the minus 8 is interesting because the number of electrons, or the density of electrons in silicon, is somewhere around 10 to the minus 10. So if it's 10 to the minus 8, that means that's like 1 out of every 100 electrons is free. Right? Am I doing my math right? I don't know if I'm doing my math right, or if I'm remembering my numbers correctly. But what I definitely remember is that you have like a kind of, that means there's enough electrons that it can do something interesting, but there's not that much electrons. So what we find, right, so here for an energy state that's like 0.045, right, that's basically what happens in conductors, right? In a conductor or in a metal, your Fermi energy is in the middle of your band, right? Conductor, semiconductor, insulator, right? In a conductor, as you saw and as you've learned previously, you have your energy bands are overlapping, and you're going to have a Fermi energy that's right in the middle, and so your energy that's right above the Fermi energy is likely to be filled, and it's available. It's right there, right? In a insulator, right? You have your bands are very far apart, right? We're talking about something like 9 eV or greater, right? Your Fermi energy is right in the middle. So that means your next available energy level is going to be up here. And so basically nothing is there, right? That's the 0.45. That's the 4.5. Your insulator is something where it has like a 10 to the minus 76 probability of being filled, which is basically zero, effectively zero. But then you have these semiconductors are in the middle, and they are far more interesting, in my opinion, that you have your Fermi energies right in the middle. And so you have your next available energy level is at maybe 0.45 eV. And so it has a 10 to the minus 8 probability of filling. And that means there's some stuff there, but not a lot. And it's enough to do interesting things. Interesting, right? And that leads to what? Solar panels, LEDs, transistors. Okay, I'm going to stop there. I can go on and on. But these statistics explain why semiconductors are super interesting. Right, so this is a big overview of what's going on with our Fermi energy, Fermi probability, probability of occupancy, occupancy probability, all of those different things, right? So you should be comfortable with this equation and doing all these calculations.